Okay, so let's begin with this video. You can hear the audio, right? Please respond. Anybody? You can hear the audio of this video?
No, sir.
You are not able to hear the audio?
No, sir.
Wait a minute.
Geotechnical engineers use their
Now?
understanding of bearing capacity to design
Okay,
systems
sir.
to safely transfer the load
Sorry?
from structures to underlying soils. The loading produces.
Are you able to hear
Yes,
now
sir,
the
we can.
audio?
Yeah.
Yes.
Yeah, I will start with from the beginning. We'll see.
Bearing capacity is the load which a soil can support without failure. Geotechnical engineers use their understanding of bearing capacity to design systems to safely transfer the load from structures to underlying soils. The loading produces compressive and shear forces in the soils. If the load is large enough, the shear forces induced in the soil will become higher than the shear strength of the soil. This results in failure. There are three types of bearing capacity failures that can occur. One type of failure is punching shear. This happens in loose sands and thin layers of strong soils underlaid by weak soils, and in weak clays which are loaded slowly. Failure develops gradually in this setting due to the high compressibility of these soils. Little to no soil disturbance is seen at the surface when punching shear occurs, but structures experience high levels of settlement. Local shear failure occurs in cohesionless and loose to medium dense soils. This failure mode has a well-defined shear surface directly under the footing that may or may not be seen at the surface of the soil. Local shear failure happens gradually as the footing continues to experience settlement and movement along the shear plane. General shear failure occurs in dense cohesionless soils and undrained cohesive soils. General shear failure is characterized by a well-defined shear plane with clearly formed disturbances in the surface soils. This type of failure occurs suddenly and can cause significant rotation of the structure. Over the years, there have been several extreme instances of bearing capacity failure. One historic event involved the Transcona grain elevator constructed in Manitoba, Canada. The elevator design had overestimated the bearing capacity of the soil and underestimated the load of the grain. This led to the structure experiencing a sudden and dramatic general shear failure. Engineers have developed methods to safely support structures and transfer loads in soils with low or insufficient bearing capacities. One method is to distribute the load of the structure over a larger surface area. Mat and raft foundations are used for this application and usually span the entire footprint of the structure for support. Another option is to bypass weak soil layers and transfer loads to stronger layers below the bedrock below. This is accomplished with deep foundations. There are several types of deep foundations which are generally categorized as driven piles, drilled shafts, and auger piles. Soil improvement can also be used with shallow foundations to get the necessary strength for structural support. Soil improvement technologies strengthen and reinforce existing soil structures at sites to increase bearing capacity. There are many different options for soil improvement, with new technologies being developed regularly.
Yeah. Okay, so that video what I shown just now was about how the different types of failure mechanism will happen in the soil. Okay, so they came in the reverse order. Okay, so they started with a punching shear, and then and then local shear, and then general shear. Okay, so how the soil will will fail in different density of depending on the density of soil, how the soil foundations will fail. If you have a very dense soil, then general shear failure occurs. If you have a moderately loose or moderately dense soil, medium type of dense sand, then local shear failure will happen. And if you have a very loose sand, then punching shear will happen. Okay, so as they told in the video, if you carefully, if you have observed that, they told in the punching shear there is a lot of displacement, you see. So the displacement is very high and very little disturbance at the ground surface in the punching shear, whereas in general shear the settlement will be less, but there will be, you can see a huge disturbance in the at the ground surface. Okay, so that is the main difference between the extreme ends of your general shear and a punching shear. Okay, so this local shear is in between the general and a punching shear. Okay, so you will see a little bit about a very small amount of disturbance, and as well as accompanied with a larger settlement. Okay, so these are the three different modes of failures in the foundation failures in the soil. Okay, so this is what we covered in our previous class. Okay, so today I'm going to start a new concept, that is Terzaghi's bearing capacity theory. Okay, so this Terzaghi's bearing capacity theory we'll discuss in today's class, and then we will see how to calculate the bearing capacity of the soil using this Terzaghi's bearing capacity theory. Okay, so let us begin with Terzaghi's bearing capacity theory. Okay, so first, before discussing any theory, so we have to see what are the assumptions he has done. Okay, so whether those assumptions are what I can say, is it intuitive or counterintuitive? Okay, so like that, whether they are acceptable or not acceptable, those assumptions. Okay, so those things we have to see first. Okay, so what are the assumptions he has done to derive this theory? First assumption is he considered a shallow foundation. Okay, so this theory is not applicable for a deep foundation. Okay, so what do you mean by shallow foundation? What is the definition of shallow foundation? I told in the previous class. What should be the criteria to decide whether the foundation is shallow? If you see this criteria, depth should be your depth of the footing. This is my ground level. Okay, so this is my ground level. My depth of the footing is less than the width of the footing. Okay, so this is my width of the footing. Okay, so then that can be considered as a shallow foundation. Okay, so the depth of the first assumption is the depth of the footing is less than or equal to width of the footing. That means it's a shallow foundation, applicable only for the shallow foundation. Then second assumption is the bottom of the footing is sufficiently rough that there is no sliding occurs between the foundation and the soil. Okay, so that is my second assumption. First, what he assumed is whatever the failure because of the sliding is ruled out here by assuming this one. So by assuming this assumption, what he is avoiding? He is avoiding any failure because of sliding. Suppose you apply a load here. Due to this applied load, see, there will not be any only vertical load will not be there, right? So always there will be some inclined load also will be there, some wind load also will be there. A different combination of loads will be there on the foundation. Due to that, what can happen? Either it may slide between the soil and the foundation. Okay, so that case he is not considering. He is considering only the vertical loads. Due to if we consider only vertical load, then only this sliding will not happen, right? So that's his second assumption. And third assumption is
Sir.
is the shear strength of soil is described by Mohr-Coulomb failure criteria. So this is the Mohr-Coulomb failure criteria. That is your shear strength is.
The screen is not shared.
Screen is not shared. Wait a minute. Okay, so can you see now the screens?
Yes.
Yeah.
Okay, so when the connection is lost, I don't know. I will anyway. I will repeat this thing. Okay, so So Terzaghi is first before deriving any theory, we have to see what are his assumptions. Okay, so first we will see the assumptions of a Terzaghi's bearing capacity theory. So first assumption is this theory is applicable only for the shallow foundations. That is, your depth should be less than or equal to breadth. Okay, so the bottom of the footing sufficiently rough enough so that there is no sliding occurs between the soil and foundation. Okay, so the bottom of the foundation is you can consider he is considered as a rough. Okay, so that he is avoiding the any sliding failure. So the third assumption is the soil beneath the footing is homogeneous, semi-infinite. Okay, so homogeneous means properties will be same, and semi-infinite means in the one direction the soil is extending to the infinity. Okay, so that means you are in the depth direction the soil is extending to infinity depth. So what is my fourth assumption? The fourth assumption is the shear strength of the soil is described by a Mohr-Coulomb failure criteria. Okay, so this is a Mohr-Coulomb failure criteria, that is shear strength of a soil is equal to the cohesion of the soil plus the vertical effective stress plus into tan of phi dash, that is your angle of internal friction. Okay, so this is the angle of internal friction, this is the effective stress on the soil, and this is the cohesion. Okay, so this is called as Mohr-Coulomb failure criteria. Okay, so the shear strength of the soil is derived from this equation. And what is my fifth assumption? He considered only a general shear failure mode. Okay, that means the soil settlement is relatively less, but it is failing by a rotational failure, and there will be a huge bulging on the ground. Okay, so that's what your general shear failure mode. Okay, he has not considered the local shear failure and purging shear failure. Okay, so whatever the formula he has derived earlier at the beginning of deriving this theory, that means at the 1943. So he considered only the general shear failure mode. So there is no consolidation of the soil when you apply the load. No, so what he considered, whatever settlement is occurring, that is due to so he has not considered the consolidation settlement. Okay, so there is no consolidation of the soil. The settlement, whatever settlement is occur of the footing, is due to only the shearing and lateral movement of the soil. Okay, so whatever movement is occurring, that is due to only the shearing and lateral movement. So that means he has not considered any consolidation settlements. The footing is very rigid, and soil is compressible. And my eighth assumption is the soil between the ground surface and a depth d has no shear strength and serves as a only surcharge load. What do you mean by that? See, whatever this soil is there, the contribution of this soil, that means above the footing. See, this is the level of your footing, right? So this is your footing, and this is your failure mechanism. So this is my failure mechanism. So whatever the contribution from this soil, he has not considered. He considered this soil only as a surcharge load. Okay, so that means gamma. Suppose this is your density, gamma into d will be acted as a surcharge. Okay, so whatever the shear resistance will be there, no, here. So against this failure, this shear resistance he has not considered. So this much amount of soil resistance he has not considered, whereas he considered the shear resistance of the soil below my footing depth. Okay, so I will change the color here. Okay, so the whatever shear resistance I am marking here, no, so this he has considered, but whereas this shear resistance he has not considered. That's what this assumption is about. Okay, so what is this? The soil between the ground surface and the depth of the footing. Okay, so where is my ground surface? This is my ground surface and depth of the footing. So this soil has no shear strength. So that means this shear strength he has not considered and serves as only surcharge load. Okay, so this whatever soil is there, this will be acted like a surcharge load here. So what is the intensity of loading here? Gamma times d. So this Q surcharge load is nothing but if unit weight of this soil is gamma and depth is d, then surcharge load will be gamma times your d. So what is the final assumption? The final assumption is the applied load is compressive and applied vertically through the center of the footing. So no applied movement and applied movements are present. Okay, so that means whatever loadings are coming on the foundation, they are exactly at the center of this footing. There is no room to apply any lateral load or any incline load. Okay, so if your foundation is experiencing this lateral load or incline load, then this theory. Okay, so this theory will work only provided these assumptions are satisfied. Okay, then only this theory is applicable. Okay, so as as science progress, what happened after 1943? See, 1943 is very long back, right? So during that time, the understanding of these failure mechanism was very limited. Okay, so that's why these all assumptions has to be made. Without these assumptions, he can't derive these equations. Okay, so it's always better to have something. Okay, so it's always better to have something rather than having nothing, right? So that's what the beginning of the bearing capacity theory has started. Okay, so in the 1943 it has started. So over the years, one by one they eliminated. Okay, so for example, like some other scientist will come and this assumption will be eliminated. Okay, what is that? What is that? Yeah, this assumption. This assumption is eliminated, and then this assumption also eliminated, and so many assumptions as the science progress, these all assumptions will be eliminated, and whatever today's equations are there, they are more realistic and more accurate. Okay, so let us discuss what Terzagh's bearing capacity theory is about. Okay, so what he considered. So this is your foundation. He considered three zones in the soil mass. Okay, so this is my depth of the footing. This is my depth of the footing. This is my breadth of the footing, and this is my load. This is my footing. So he considered three regions. Okay, so first this is zone 1, and this is zone 2, and this is zone 3. Three zones he considered. So first zone is called as a wedge zone. So this wedge zone, see, Terzaghi considered three zones in the soil immediately beneath the footing. Footing is a wedge zone. Okay, so this is the wedge zone. So that remains intact and moves downward with the footing. Okay, so what will happen once you apply the load on the footing? What will happen? It will start with the small settlement. Okay, so the small settlement will happen. So then what will happen? Immediately below the footing, whatever this much soil is there, no? First this much soil will be filled and it will become a part of this foundation. It will become like a part of foundation, and now whatever settlement will happen, that settlement will happen both your foundation as well as this chunk of soil. Both together will penetrate as you keep on increase the load. Okay, so then what will happen next? A radial shear zone will develop. What is mean by this radial shear zone? This zone will develop. Okay, so this green part. The next, the radial shear zone will extend from each side of the wedge, where it took the shape of the shear plane to be logarithmic spiral. Okay, so this failure is there. This shape we consider it as a logarithmic spiral. Okay, not a circular one. It's not exactly circle. It's a logarithmic spiral. See the same. See, I have shown the zones only on the one side of the footing. Okay, so the same holds good even in the left side also. Here also the same zone will be there, like this zones will be there. I have shown only on the one side because it's a symmetry, right? So it's symmetric about your y-axis. Okay, so whatever zones are present, they are present on the your right side also. So and what is the third zone? Third zone is the passive zone. So finally, the outer portion of the passive zone is the passive zone. Okay, so this is my passive zone, or it's also called as linear shear zone, in which the soil shears along the planar surface. Okay, so here the soil is failing planar surface. You see here, if you see the failure surface, this is the failure surface. Okay, so this is the planar surface, but here it is a log spiral surface. Okay, so this is the log spiral surface. this is what the 3-zone concept. Okay, so first zone is your wedge zone, and second zone is the radial shear zone, and third zone is the passive zone. So the solution obtained originally by Terzaghi was for stiff footing. Okay, so whatever the footing he considered, no, here in the derivation, this footing he considered for the stiff footing. What do you mean by stiff footing? The length will be very high, very large compared to the width of the foundation. Okay, so if I 3-dimensionally, if I want to so this is the stiff footing. So your breadth dimension is very small compared to the length dimension. This is my length. That's what your that's called as stiff footing. Okay, so whatever derivation he started with a stiff footing, that is those with a very large L/B ratio on the surface of the homogeneous soil. And for footing embedded in the ground, the effect of overburden pressure is taken care by this gamma times your D. Okay, so whatever this this subcharge pressure is, that will be taken care by your Q value. The solution was modified to include footings of different shapes, like a square, circular shapes. Okay, so then he later on he worked on the that stiff footing, and then he introduced some shape factors so that they can include the even for they can these theory can be applicable even for this square and circular footing. So this is the formulas from the Terzaghi's bearing capacity theory. Okay, so for continuous, if you have a continuous stiff footing, then you should use this one. That is ultimate bearing capacity of the soil, Qu is equal to cohesion term, C is the cohesion term, into Nc. So what is Nc? I will come to that later. Okay, so plus Q times Nq. What is the Q here? Q is the surcharge load. Okay, so this is my Q. Q times Nq plus 0.5 gamma times B into N gamma. Okay, so this is for continuous footing, and if you have a square footing, this is the formula, and if you have a circular footing, this is the formula. You have to remember. Okay, so only what it is changing here, only some coefficient numbers are changing, but the basic equation is same. Basic equation is same, only the basic coefficients are changing here. 1.3 is coming extra, and 0.4 is coming extra here. So this is for stiff footing, we will use 0.5. For square footing, we will use 0.4, and for circular footing, we will use 0.3. So what is Q? Q is nothing but ultimate bearing capacity, and C is the cohesion, and gamma is the unit weight of soil, and Q is the surcharge, that is overburden pressure at the level of the footing base, and B is the width of the footing. Okay, so this Nc, Nq, N gamma are the bearing capacity factors. We will call these as a bearing capacity factors. Okay, so which are a function of your these angle of internal friction. Okay, so this Nc, Nq, N gamma are there. No, these are the function of your phi value. Okay, so that is the angle of internal friction. So how to get these values, Nc, Nq, N gamma? There are 3 different ways to get these Nc, Nq, N gamma. Okay, so one thing, yeah, before going to the Nc, Nq, N gamma, I will just explain what is who is contributing this one, and who is contributing this term, and who is contributing this term. Okay, so this first term is contributed by your cohesion of the soil. Okay, so whatever this first term is there, no, this term is contributed by the cohesion of the soil. Okay, so whatever soil cohesion property will be there, no, that will contribute to this first term. And this second term, that is Q into Nq, is there. No, this is contributed by by the frictional contribution from the overburden pressure. Okay, so that means whatever soil is present here, whatever soil is there, no, here, this soil is contributing for this second term. And what is the third term? This third term is contributed by the soil present below your footing. Okay, so whatever soil is present below the footing, that is contributing this third term. Okay, so this is my first term, second term, and third term. So first term is contributed by the cohesion of the soil. Second term is contributed by the angle of internal friction of this the soil present above the depth of the footing, and a third term is contributed by the soil present below the footing of the footing, this footing. Okay, so that's whatever phi value is there, no, here, that is contributing the third term. Whatever phi value is here, that is contributing my second term. Okay, so whatever cohesion term is there, that is contributing your first term. Okay, so now we'll see how to get this NC value. Anyway, C and phi will be found out from your laboratory test. Okay, so in the soil exploration, what you would have done, you have taken out the soil sample from the footing, and then you have tested in the laboratory. Okay, so from the laboratory you will get your C value and phi value. Even we have some institute tests also to get C and phi value in the field itself. Okay, so there are two ways to find out this C and phi value. One is by laboratory test, and another one is by doing some institute test in the field itself. Okay, so those institute tests I will discuss in the second part of this lecture. Okay, anyway, these laboratory tests we will discuss in the next semester. You have a lab. In that lab, we will discuss how to find out these C value and phi value from different types of for different soils in the laboratory. Okay, so now you know now what are the inputs parameters for these equations. First input is C and phi value, which can be obtained from your either from lab or from the institute tests. Okay, once you get C and phi value, the next inputs are your NC, NQ, and N gamma parameters. So how to get those parameters? Again, this NC, NQ, N gamma are there, no? This NC, NQ, and N gamma. Okay, so these parameters are dependent on your phi value. Okay, so there are three ways to find out. Either they are provided in terms of table, or in terms of charts, or in terms of formula. Okay, so there are three ways to find out your bearing capacity factors. Okay, so these are the bearing capacity factors. So what are the bearing capacity factors? That is NC, NQ, and N gamma. So how to find out these bearing capacity factors? I have three ways. One is I can use the tables, or I can use the charts, or I can use the formulas. Okay, so let us see the tables. Okay, so you see this table. This table, for different phi value, they will provide you NC value, NQ value, and N gamma value. Okay, so these are the bearing capacity factors from Terzaghis theory. Okay, so in the same way, even in the later part of this, in the 1973, one more scientist, that is Vesic. So Vesic also, what he did, he worked on the the Terzaghis bearing capacity theory, and he also proposed some theory based on he also improved this Terzaghis bearing capacity theory. Okay, so that I will discuss in the later part of this lecture. What do you mean by what is actually the Vesic theory is? Okay, so for time being, you don't concentrate on this table. Okay, so you concentrate only on this table. So for the different phi value, I have NC value, NQ value, and N gamma value. Suppose my from the laboratory test, if I found out my phi value is around 8 degree, then I have to take NC 8.6, NQ 2.2, and N gamma 0.7. Okay, so like that. See, here in this table I shown only up to phi value of a 9 degree. Okay, so but if you refer to IS 6403. So IS 6403 or some relevant textbook, they have provided these phi value for all the up to 40 degree, 35 degree, or 40 degree. They have given these NC value and NQ value and N gamma value. Okay, so in the examination they will give you a phi value. For that corresponding phi value, they will give you the NC value and NQ value and N gamma value. Okay. So this is one way of finding out one way of obtaining this NQ and N gamma. So what is the second mode of obtaining your NC, NQ and N gamma? So by looking at this graph, okay. So you see for different phi value, I have NC value, NQ value, and N gamma value. Okay, so suppose if I want, if my soil is having some 35-degree angle of internal friction, then what is my NC value? Where is my NC curve? This is my NC curve. Okay, so this is my NC value. So what is 50? So around 60. So this is my NC value. What is my NQ value? So for 30-degree, so this is my NQ curve. Let me change the color here. So this is my NQ. Okay, so this is my NQ. So where is my N gamma? So N gamma curve is this one. So this is my N gamma. Okay, like that I can obtain the these bearing capacity factors. So what is the third alternative? Third alternative is they have given some equations. Okay, so for NC and if for NC for phi equal to 0, you can take this equation, and for phi greater than 0, you can take this equation, and for NQ you can use this equation, and N gamma you can use this equation. Okay, but you need not to remember. Okay, so you note here what I written here. You need not to remember these formulas. In exams, NC, NQ, and N gamma will be provided. Okay, so you don't bother. So just I shown these equations just for the completeness purpose. Okay, so no need to remember these equations. Okay, no need to remember these equations. Always this NC, NQ, N gamma will be provided. Or if they not provide, then what they will do? They will allow you to carry IS 6403. I will come to that part. IS 6403. Okay, so if they allow you to carry this 6403, then no need to remember even. They need not to give NQ, NC, and N gamma values. Okay, so directly you can refer to that 6403, and in 6403 we have table 1. So table number 1. If you refer table number 1, these values you will get: NC value, NQ value, and N gamma value. Everything you will get. Okay, so previously whatever these formulas we discussed now, so these are for what assumption he did. You remember the assumption. This assumption, if you remember, this is general shear failure mode. Okay, so initially he developed for general shear failure mode, then he modified even for the local shear failure mode also. Okay, so we'll see now what it will change in the local shear failure mode. Okay, so now the same Terzaghi's bearing capacity theory for local shear failure. Previously we have discussed for the general shear failure mode. Okay, so if you see for stiff footing, for square foundation, and for circular foundation, these are the formula you should use. Okay, but if you recall, if you write both equations side by side, there will not be any much difference. Okay, so only some coefficients will change here. Only some coefficients will change, but the basic format is same. CNC, QNQ, gamma B and gamma, basic format is same. Only some coefficient value will change here. And you see this NC dash. See, earlier I used NC, NQ, and N gamma I used, right? Here I am using NC dash, NQ dash, and N gamma dash. So these are nothing but these are the bearing capacity factors for the local shear failure. Okay, again these are also function of what? Function of your angle of internal friction, phi value. Okay, so to obtain NC dash, NQ dash, N gamma dash, we have to convert this phi value to phi dash value. you have to convert whatever phi value is there, that you have to convert into phi dash. Then for this phi dash value, you look for this NC, NQ, N gamma value. That itself will become NC dash, NQ dash, N gamma dash. Understood now? See what I am telling. I will repeat it once again. What you do first, whatever phi value is there, you take that phi value, then you convert this phi value to phi dash value. How I can convert a phi to phi dash? By using this equation. So my phi dash is nothing but tan inverse of 2/3 of tan phi dash. Now I got phi dash value. For this phi dash value, you take NC, NQ, N gamma value. Those itself will become NC dash, NQ dash, and N gamma dash. That means you are reducing what you are essentially doing. You are essentially reducing your phi value. You are reducing the phi value, and for that reduced phi value, you are looking for bearing capacity factors. Those will become your bearing capacity factors for the local shear failure. Is there any confusion here? Am I clear here? Whatever I am explaining. Please respond. Anybody, if you understood, then I will continue. Otherwise, I will repeat it. Any confusion here? How to get is NC dash, NQ dash, and N gamma dash values? Any doubts?
No, sir.
No doubt. Aishwarya, brother. Any
No,
doubts?
sir.
No. So, see, till now what we did, we discussed the Terzaghi's bearing, the assumptions of a Terzaghi's bearing capacity. Then, initially what he did at Terzaghi in 1943, he started with the only general shear failure and a strip footing. Okay, so whatever his initial derivations were there, they were applicable only for the general shear failure case and for strip footing. Later on, he himself, what he did, he always humans will evolve over the period, right? So what your understanding capacity was there in the first semester, now it's better than your first semester, right? Your understanding capacity. So like that, once that Terzaghi understood his limitations, then he improved over that equation. Okay, so first he started with general failure case and for the strip footing. Then what he understood, okay, there are local shear failure also is there. Then how to find out the bearing capacity for those local shear failure criteria. So what he introduced that NC dash, NQ dash, and N gamma dash bearing capacity factors. Okay, so how to get those reduced bearing capacity factors? By reducing your phi value. Okay, so by reducing phi value, whatever phi value will reduce, for that phi value you have to look for NC, NQ, N gamma value. Then those numbers will become your same numbers will become your bearing capacity factors for the local shear failure also. Okay, so for timing, you remember like this. Okay, so once we solve what I will do, I will take same problem. I will solve with by considering it as a general shear failure case, and then by considering it as a local shear failure case. Okay, then we will see how it will change while calculations. Okay, once we apply that same concept in some actual problem, then whatever theory we have learned, that will be more clearer for you. So when is your next class? I hope still I have time, right? So please let me know when your next class will start. So this is these are the formulas we should use for the local shear failure case. Okay, so here one problem is there. Okay, so this problem we'll see, and then see how these different shapes will change my bearing capacity. Okay, so now this problem is only for the general shape case. Okay, so here sorry, this is 30 degree, not 300. 30 degree. So calculate the bearing capacity for different types of foundation given below. So based on the Terzaghis bearing capacity, he is asking. So my phi value is 30 degree, and your dry density of the soil is 18 kilonewton per meter cube, and the depth of the footing is 2.5 meter, and my cohesion is 0. Okay, that means I have only sandy soil. Okay, so let me draw the figure here. So here, this is my foundation. This is my ground level. Okay, so this is my depth of the footing. Depth of the footing is how much? 2.5 meter. And what is the cohesion of the soil? Cohesion is 0 kPa. And what is the angle of internal friction? Phi is 30 degree. Phi value is 30 degree. What he is asking? He is asking to find out the bearing capacity for 3 cases. There are 3 cases. First case is by considering this as a stiff footing. Okay, case 1. This is case 1. Assuming this as a stiff footing, and assuming this as a square footing, and assuming by this as a circular footing. Okay? This is for circular footing. This is for the square footing, and this is for the stiff footing. Okay. So what are the formulas I should use? So now I am talking only the general shear case. So for time being, you forget about that local shear. Don't you forget about local shear. I will stick to only the general shear failure case. What Terzaghi earlier in the initial stage he has derived. So in the general shear case, see what I am using only NC value, NQ value, and N gamma value. So for the continuous footing, I should use this equation. For square footing, I should use this, and for circular footing, I should use. Okay. So here, what are the inputs? C anyway 0. Okay. C anyway 0. So NC I don't know. NQ also I don't know, and N gamma also I don't know. How I can find out these NC, NQ, N gamma? These are the functions of what? NC, NQ, and N gamma are functions of your phi value. See, for different phi value, I have NC value, NQ value, and N gamma value. So what is the phi value in this problem? In this problem, phi value is 30 degree.
30.
Okay? Yeah. For 30 degree, corresponding NC, NQ, N gamma, you see, NC is the 37.16, and NQ is 22.46, and N gamma is 19.13. See, I have first for the stiff footing I am calculating. Okay, so this is the equation for the stiff footing. Okay, so this is nothing but Q value. This is sigma, whatever sigma is there. This is Q value. So what is the C dash into NC plus your Q into NQ plus 0.5 gamma B N gamma. Okay. I think C value, I think they given 5 kilopascal. Just a minute. Here 0 kilo. It's not 0. Here 5 kilopascal you take. This is not 0. C value is 5 kilopascal. C is equal to 5 kilopascal. So I think I misprinted here. So while printing here, I made some mistake here. So this is 5 kilopascal. C is 5 kilopascal. And your phi is 30 degree. Okay. So what is my C value? 5 kilopascal. What is NC value? NC value from the table 37.16. 37.16 almost equal to 37.2 into Q. This term is Q term. Q into NQ. NQ how much? 22.5. You see, this is the 22.5. So this is my NQ, and half into gamma P N gamma. Okay. So what is the unit weight of soil? Unit weight of soil is 18. That's what 18 I put. And what is the width of the footing? 2.5 into N gamma. N gamma again from the table, 19.13. So what is Q here? Q is nothing but the overburden pressure. So at this level, what is my Q? So here, this is my Q value. This Q is nothing but water. Q is nothing but whatever soil present above the footing. So depth of the footing times the unit weight of the soil. 2.5 times unit weight is 18. 2.5 times unit weight of soil, that is 18. So this term is Q value. So I got, for the stiff footing, how much I got? Around 1622 kilopascal. 1622 kilopascal. For the same soil profile and for the same condition, now if I have a square footing, how it will change? For the square footing, this is the formula I should use: 1.3 C NC dash Q NQ plus 0.5 gamma B. 4 by 10 means that's what here, 0.4. So this is the formula I should use, and see, this 4 by 10 is nothing but 0.4 only, no? This is 0.4. And this is 0.3. So if I use, if I have a square footing, then what is the bearing capacity I am getting? This much bearing capacity I am getting. No? How much? 1598. A little bit lesser than your stiff footing. And if you have a circular footing, 1512 kilopascal. Still lesser than your square footing. Okay. So what the conclusion I can draw, for the same condition, if you change the shape of the footing, then your bearing capacity is changing here. For the stiff footing, we are getting highest bearing capacity, and a square footing a little lesser than my stiff footing, and for the circular footing, still lesser than my continuous or stiff footing and square footing. So understood? Any doubts here? So this, whatever problem I solved, it is for general shear case. General shear failure case. General shear failure case. So for the same thing, if you assume it as a local shear failure case, what it will change? It will change your NC term, NQ term, N gamma term are there. No, those only will change. What they will become? They will become NC dash, NQ dash, and N gamma dash. But how to judge whether soil is failing by general or local shear? How I can judge? By looking at the phi value. By looking at the phi value, I can judge whether the soil is going to fail in general shear or local shear. Okay. So in practice, what you will do, if my phi value is greater than 35 degree, if my phi value is greater than 35 degree, then I will consider it as a general shear failure case. If my phi value is less than 35 degree, then I will consider it as a local shear failure case. Okay. So in the problem, if they mention that assume it as a general shear failure case, then you proceed as it is. Okay. If they not mention how the soil is failing, okay, so then what you have to do, you look at the phi value. You look at the phi value, and then you see whether it is more than 35 degree or less than 35 degree. If it is more than 35 degree, then you should mention there clearly. You should write, since phi value is greater than 35 degree, so assume the soil is failing by a general shear case. Okay, so if the phi value is less than 35 degree, then you have to write clearly, assuming it as a local shear failure case. So whatever your assumptions you are doing, that you should write it clearly in the examinations. Okay, so accordingly, the evaluator will understand that whether because there is no one answer for this. Okay, so some people, if they assume it as a general shear failure case, then you will get a little different answer. If you assume it as a local shear, then you will get a different answer. Okay, so that's why you have to write it clearly in the exam. So I am assuming it as a local shear failure case, or I am assuming it as a general shear case. Okay, so you should write the whatever the assumptions you are doing, you should write that clearly. Even in the examination also, they will in your VTU exam, they will write in the note. So whatever assumptions you are doing, you are assuming, you have to mention those assumptions clearly in the answer sheet. Whether your next class is scheduled? I think so, right?
Yes, sir.
Yeah. So I will end the meeting here. So I will again, so maybe tomorrow we'll see the remaining portion.